What is a unit circle? A unit circle is a circle that has a radius of 1 unit. Remember, we're talking about polar graphing here. And with polar graphing, it's like chess and checkers where you have different rules along the same kind of board. Now we call this 0 degrees, we call this 90 degrees, we call this pi, and we call this 3 pi over 2. But when you talk about these angle measures, don't forget that we also used to use x for this axis over here and y for the vertical axis up and down. So keeping in mind that there's an x and y component to the same kind of graph that has a theta and a r component, that must mean that if I were to pick a point out somewhere on this graph, not only should I be able to give you an r theta version, but I should also be able to give you xy version. We call that the rectangular coordinates. So rectangular and polar coordinates, there should be a way to convert them with each other. So let's say, for example, we have a radius of 1, because I did say we're not worried about radii bigger than 1. However, I'll show you some examples. And I told you this angle measure was pi over 6. The question is, how can I give the xy coordinates of this point with the information of r and theta? Well, remember, rectangular coordinates are all about getting to your point by traveling horizontally and then vertically. And if you know how far you went horizontally, that'll give you your x value. And if you know how far you went vertically, that'll give you your y value. Now, this is a special right triangle. Don't forget that we have a special right triangle because pi over 6 is 30 degrees, so it gives you the pi over 6, pi over 3, and pi over 2 right triangle. So since the hypotenuse is 1, that must mean that the pi over 6 side is 1/2, which must mean that the pi over 3 side, because if this is pi over 6 and this has to be pi over 3, the pi over 3 side has to be root 3 over 2, because you multiply the pi over 6 side by root 3 to get it, which now gives us a rectangular coordinate of root 3 over 2, comma, 1/2. Why is a unit circle useful to us in this context? Because all right triangles are similar if the angles are the same. So let's say, for example, I were to try to find the same thing where we have a right triangle and the angle is pi over 6, but the hypotenuse was 3, aka the radius of our circle was 3 instead. This would become 3 over 2. This would be 3 root 3 over 2, because remember you divide by 2 to get from the pi over 2 side to the pi over 6 side, and then 3 root 3 over 2 because you multiply by root 3 to go from the pi over 6 side to the pi over 3 side. So we get the same information, but when you think about the division of it with trig functions, this is where it really becomes useful. Let's talk about what this has to do with trig functions. Well, if I have, for example, a right triangle, and this is 3, and we're going to transfer that same one that we just did over here. So this is 3 over 2, and this is 3 root 3 over 2. And it asks you to find the sine of pi over 6. Well, you know it's this opposite side divided by that hypotenuse side. So it's 3 over 2 divided by 3, which gives you 3 over 2 times 1 over 3, which gives you 1/2. But guess what? We did all this work to get to 1/2. When back here, the 1/2 was easy to find because you divided it by 1. In this situation, if I did sine of pi over 6, I would do the 1/2 that I found over here and divide that by the 1, but it's easy to divide by 1. You know the value doesn't change, so you get the 1/2. So the power behind the unit circle is that it allows us to evaluate all of our trig functions over a hypotenuse of 1. But you'll also notice that the 1/2 that we got matches the y coordinate of what we have over here. If I asked you to find cosine of pi over 6 instead, then that would lead us to doing the adjacent side, which is root 3 over 2. And you know the hypotenuse is 1 anyways, so that just ends up being root 3 over 2. So what's the benefit? Unit circle over 1, it makes the rectangular xy coordinates equivalent to the trig functions themselves. How can we prove that? Let's create a circle. And when we're proving anything that's general for everything, we have to make sure that we're using variables because we do not want something to only work for numerical values. We need to work for all values instead. So let's say I create a right triangle such that this adjacent side is going to be x. The vertical side here, the opposite side, is going to be y. Hypotenuse is going to be 1 because we're doing this off a unit circle. So this is under the assumption that we work with the unit circle, which doesn't matter because all circles are going to be similar and all triangles with the same angle measure are going to be similar as well. So a unit circle represents everything we're doing trig functions because of the ratio aspect of it. If I ask you to find sine of theta, well, that's just going to be y over 1. So it's y. It's the y value of this xy coordinate. If I ask you to find cosine of theta, that's going to be x because it's the adjacent side over the hypotenuse. And then if I ask you to find tangent of theta, well, that's going to be opposite over the adjacent side. So that's going to give us y over x. So it's all straightforward right now how you can use the right triangles to get trig functions. And of course, it works the same way for the reciprocal functions. And note that that means that this must be true for pretty much everything. So if I do cosecant of theta, that means I should be getting 1 over y. This should be 1 over x. And cotangent theta should give you x over y. Now, let's say I were to draw the same right triangle in quadrant 2. In quadrant 2, we would be actually changing the way we kind of see this a little bit. Because in quadrant 2, our theta value is here. To go to quadrant 2, you would need an angle measure like 120 degrees, for example. So when you have quadrant 2 angles that are pretty much the same thing in terms of the triangle angle here as what you would have had over here, and we're going to just call this alpha to help make the differences distinct, then what's really going to be happening is this right triangle on the left right triangle, should have the same values as the right triangle we had on the right. So if we call this x over here, then the green triangle on our left, the alpha triangle, the one that we had, or the theta triangle, should be x as well. And if this triangle on the right, the fuchsia one, vertically, we call that y, then on the green triangle, it should be y as well, because we're still working with the unit circle. But coordinate-wise, it's not the same, because it doesn't make sense that this triangle on the right side has x comma y, when on the left side we also have x comma y, because that's suggesting that if this coordinate right here was like 1/2 comma root 3 over 2, that means I'm saying over here it's also positive 1/2 comma root 3 over 2. But that's not possible because the x sides over here, the x value should be negative. So really on the left side, then what you're going to get are negative values. So in quadrant 2, your x values should be negative. And then that will lead us to quadrant 3, where instead of having only a negative x value, you should be having a negative x and a negative y value. And lastly, in quadrant 4, you should be having a positive x but a negative y value instead. So there are even and odd functions at play. And also we have to remember that there's differences in when an angle is going to be positive or negative. And that leads us to our next two things. Let's start by doing some practice in quadrant 1 and then doing a little practice on quadrant 2. So for the first practice problem, this is the one I expect everyone to be able to do right now. Find the rectangular coordinates of pi over 3 on the unit circle. And then the second one, which I don't expect everyone to do right away, is find the rectangular coordinates of 2 pi over 3 on a unit circle. Go ahead and pause the video. So if you're trying to find the rectangular coordinates of pi over 3 on a unit circle, which will give us the trig function values, because don't forget the x and y coordinates of a trig function give us sine and cosine of theta. What you would have to graph is pi over 3. So we start at 0 degrees because that's standard position. We go pi over 3 counterclockwise because that's a positive angle measure. And that'll give us pi over 3 here. Remember, we need to find the vertical distance and the horizontal distance to get our rectangular coordinates, aka x comma y. So to get our rectangular coordinates, we then have to figure out, okay, that's pi over 3, unit circle means the hypotenuse is 1. Pi over 3 side should then be root 3 over 2. And that means this side over here should be 1/2, because the pi over 6 side is always half of the pi over 2 side. So that gives us a coordinates 1/2, comma root 3 over 2. For this one over here, find the rectangular coordinates of 2 pi over 3 on a unit circle. This one's much more challenging. We have to go 2 pi over 3. Now, 2 pi over 3 is greater than pi over 2. 2/3 is greater than 1/2. So that's 0 degrees here. This is pi over 2 up here. We're going to go a little further and then draw that line to represent 2 pi over 3. Now, this doesn't give us a right triangle of which to get angle measurements. But if you ask yourself, how can you reach the x and y coordinates of a point that's in quadrant 2? You have to go left first, and then you have to go up. And in doing that, we created a right triangle. So that means when you have a quadrant 2 angle, your right triangles are always going to look like this. So now we went 2 pi over 3 to get this far, but that doesn't help us. We really need the angle measure that's located here. That's the angle measure that we really need to have. Don't forget, this whole half circle is pi. It's 180 degrees, which means if I went 2 pi over 3 to get to this part, the amount that's remaining is pi over 3. Okay, so now that I know this is pi over 3, that means this is pi over 6, which allows me to start labeling the lengths. The pi over 6 side is half the hypotenuse, and the hypotenuse is 1 long, so this side is 1/2, and that's root 3 over 2. But don't forget, at this moment in time right here, you can label whether it's positive or negative. From the origin, we went to the left, which means this is negative 1/2. From here, we went up, which means this is positive root 3 over 2. And your hypotenuse is a length, so your hypotenuse must always be positive. Hypotenuse is always positive because it's the radius, and the radius cannot have a negative measurement. So that means our x-coordinate is negative 1/2, while our y-coordinate is root 3 over 2. What this means is, if I ask you to find sine of 2 pi over 3, we created this triangle to find this y-coordinate, which makes it root 3 over 2. Because sine is the opposite side is right here, it's the vertical length. So we created two things in order to do this. The first thing we created is a reference triangle. The reference triangle is always created using the horizontal line, the x-axis. A reference triangle is a triangle that is created using the x-axis, aka the horizontal line. And just like a lot of things in life, we use a horizontal line. Angle of elevation, angle of depression, we are always focused on the horizontal line. The central angle, which we mark as theta, is the given angle, the angle we are using or trying to find. And that given angle should always also be the reference angle. Over here, for the reference angle is the angle you're actually using in your special right triangle, or not even special, but it's the actual angle you're using in your reference triangle. So over here, when we had 2 pi over 3, 2 pi over 3 was not a reference angle. 2 pi over 3 is the angle we're actually trying to find. The reference angle is pi over 3 because this was the angle we referred to do all of our side length measurements. Without pi over 3, we would never have known that was negative 1/2. So actually I made a mistake here. The central angle is the reference angle. It's not the given angle. My apologies on that error. So again, the reference angle is the central angle. No, it's not, sorry. The reference angle is the angle used in our reference triangle to calculate and evaluate trigonometric expressions. Now, there is a defined value that your reference angle can be. Your reference angle has to be less than 90 degrees, greater than 0 degrees. You can also say that it is less than pi over 2 or greater than 0. So let's just do a practice of drawing a reference angle. Let's ask you to draw that reference angle of 315 degrees, which is the same thing as 7 pi, sorry, not 7 pi, which is the same thing as 11 pi over 6. No, it's not. It's the same thing as pi over 4s, so you're going to have 8 pi over 4, 7 pi over 4. If I go 315 degrees around, that gets us to here. But 315 degrees is not the reference angle. The reference angle is that little section that we're going to use to create our reference triangle. Remember, your reference triangle must always be created using the horizontal line. So that means we have to draw this line up to here. So this is our reference triangle, and the blue line is going to be our reference angle. That means our reference angle value here is going to be 45 degrees. Why is that useful? Because now we can figure out the coordinates using a 45, 45, 90 degree right triangle. If this is going to be 45 degrees for 315 degrees, and the unit circle makes that 1, that means the coordinate is going to be root 2 over 2, comma root 2 over 2. Again, you can figure that out using special right triangles. Let's say, for example, I want to do another one, and I asked you to, let's say, maybe do negative 225 degrees. Actually, let's do negative 135 degrees. From 0, standard position, we are going to go clockwise now, which gets us to here because it's less than 180 degrees. Again, we know the radius length has to be 1. We're going to draw a line to the horizontal because we always use a horizontal line, which means that if we travel 135 degrees this way clockwise, the remaining angle, which will give us our reference angle, is going to be 45 degrees. Now, because that's 45 degrees, you divide by root 2, so that's going to be 1 over root 2, which is how we got root 2 over 2, because we have to rationalize the denominator. And we already know that because this is going left, this is negative. And because it's going down, this is negative. So our coordinates here are going to be negative root 2 over 2, comma negative root 2 over 2. Which makes this very easy if I ask you to find tangent of negative 135 degrees. Because that's going to be your opposite over your adjacent, which is negative root 2 over 2, divided by negative root 2 over 2, which gives you 1. Go ahead and practice with these two problems over here. I'm only asking you to find the Cartesian coordinates, but you are going to need to use reference triangles to do so. And there's a little bit of a trick here because that will give us a tip for later on. Go ahead and pause the video. When you're finding the rectangular coordinates of 5 pi over 4 in a unit circle, 5 pi over 4, an easy way I think of radians is I know this right here, all the way around, is 4 pi over 4. So 5 pi over 4 means I have another pi over 4 extra, which means that I should be going around to quadrant 3. Now, because I'm at quadrant 3, this will allow me to create a right triangle going this way. 5 pi over 4 means that I have an extra pi over 4, which is why this is pi over 4 as my reference angle. If that's 1, that makes this negative root 2 over 2, and that makes this negative root 2 over 2, which means that my coordinates are going to be negative root 2 over 2, comma, negative root 2 over 2. And note that this is the exact same coordinate as what we did over here, which means that 5 pi over 4 is coterminal with negative 135 degrees. They are coterminal angles. For the next practice problem, find the Cartesian coordinates of negative 7 pi over 6 on a circle with a radius of 2. There's a reason why I gave you a radius of 2 this time. Negative 7 pi over 6. So remember, half the circle around is pi, which is equal to 6 pi over 6. So since we're going 7 pi over 6s, we're going a little extra. So I'm going to go 6 pi over 6 and a little extra, which gets me to quadrant 2. But this time, this radius, because remember the radius is the same thing as the hypotenuse, so your reference triangles, is 2. So now, if I go 6 pi over 6, this extra part is now pi over 6, which makes this pi over 3. I know that the pi over 6 side is half the pi over 2 side, and it's easy to divide 2 by 2, it's 1, which makes this root 3. That would make the coordinate here actually root 3 comma 1. What was the mistake I made? Find the mistake. The mistake was I forgot to put a negative here on the negative root 3 because it's in quadrant 2. The x value cannot be positive. So we got negative root 3 comma 1. Now, why is this useful? Well, it's not useful right away for finding sine of negative 7 pi over 6. Because usually we could just take the y coordinate and make that the answer. But we know that's not the answer here. Because remember, this is the same thing as opposite over hypotenuse. So it's 1 over 2, which makes it 1 over 2. So it's 1/2. But keep in mind that you could still get 1/2 using a unit circle. In the next video, you'll see why this is my preference.